out here, you can controllably couple between them. So this is the ground state of this 87 rubidium atoms, and this is the Rydberg excited states, and this is controllably coupled by through an intermediate state whose details are not here, but I mean these are some atomic states. Okay. So the interesting part about this is that once these atoms get excited to their Rydberg state, they have strong van der Waals interaction between them, and this leads to a 1 over R6 kind of potential between two Rydberg excited atoms. Okay. And also there is a tuning parameter called delta, which originates from this atom laser physics, which you can tune in order to preferentially put an atom in either a Rydberg or a ground state. And in this, throughout this talk, we are going to adopt the sign convention where delta being large and positive favors Rydberg excitation. So this delta detuning parameter acts as a chemical potential of the effective model. It just tells you how easy or difficult it is to make an atom excited to its Rydberg state. This tells you that if you put these two Rydberg atoms which are at sites I and j in their Rydberg state, then you are going to have a repulsive potential between them, and this omega is coupling between this Rydberg and the ground state. Okay. So this is the model that we are going to talk about. So people have looked into the phase diagram of this model, and interestingly there is some work in 2017 when these Rydberg chains are controllably tuned between a Rydberg vacuum, which is out here, where there is no Rydberg excitation, to some Z2 state. And why this can be done is that if you look into this, if you look into this model, if you make your V, which is this V naught parameter, to be large enough, you can enforce a constraint that there will be no two Rydberg excitation in neighboring sites, because that energetically too costly. And once you do that and then you put delta to be large and positive, what happens is that the system wants to create as many Rydberg excitations as possible. However, they can only create it at next neighboring sites, because this van der Waals interaction prohibits creating Rydberg excitation from neighbors. And as a result, there are two ways of doing it. You can either create these Rydberg excitations on the odd sites or the even sites, and therefore this ground state begs Z2 symmetry, and therefore the vacuum is separated from this state by an Ising transition, because it's a Z2 symmetry broken state. So in a slightly different context of tilted optical, that is, we worked on this quite a bit in the past. So one can map this Rydberg model to a constraint model. So one can say that there are two states per site, which is given by this sigma. So you can define a sigma z depending on the number of Rydberg excitation, and one can also define a projection operator which just projects a spin in this language to down state, that is, project the atom to its vacuum. Now the point is that to enforce the Rydberg constant, what one does is to say that I can only flip a spin on a given site provided the neighboring spins are down, and only then I can create an Rydberg excitation, and this allows me to basically throw away configurations which have neighboring up spins. Okay, and that's the Rydberg this PXP subspace. So you can do some math and you get a thing like this, where you have a term lambda times sigma z, and then there is some W coefficient times sigma tilde, where the sigma tilde is a sigma operator which is flanked by two projectors. Okay. So in whatever follows, we are going to sort of drive this by making lambda of t according to a square pulse protocol, and W also according to a square pulse protocol, but with a shift. Okay. So to digression, maybe I'll skip this. This is some perturbation theory that we use, and it can be done. It's some standard perturbation that one works, and when you apply that to the Rydberg system, what you find is that you can calculate the evolution operator of this driven system, and from there compute a Fluke Hamiltonian. Interestingly, this Fluke Hamiltonian has points which corresponds to this parameter gamma, which is lambda, which is basically some combination of the frequency and the drive amplitude. When this goes to some integer multiple of pi, this Fluke Hamiltonian vanishes, and this will be important for our studies later on. So now I am going to talk about how to arrest heating in a two-rate protocol using this two-rate protocol. Now, arresting heating in a periodic drive has a rich history. So, people have looked into, so what happens when you drive a system is that it simply spreads in Hilbert space, and therefore the entanglement grows unboundedly, and the system reaches an infinite steady state. And because, this is typically called a heat death, because you cannot retrieve any information from that system anymore through some local measurement. So, any information contained in the initial state gets completely scrambled, and this is due to the rapid spread of the state in the Hilbert space. And this heating is something that one needs to arrest if one needs to get meaningful information out of that state. So, there are several ways of this. So, Berry came up with some counter diabatic driving, where you keep adding terms to this Hamiltonian so as to make the make the system go a near adiabatic evolution. Or people do something called optimal protocol, where they tweak the parameters of this Hamiltonian as you go by during driving. And unfortunately, both have their difficulties for implementation of experimentally. This here, essentially what happens is that as you when you add these terms, you often find that for a realistic model, these terms would be non-local, and in optimal protocol, it's simply too complicated to keep tweaking your parameters on the fly, as you go on. So, the suggestion that we get is that we can use a two-rate protocol, which is experimentally more viable. Now, what does this do? So, now we consider a generic non-integrable Hamiltonian, which is driven with some coefficients lambda I, which is a function of time, and these can have different protocols. So, for example, and there are two such operators. These operators can be completely generic. They can be short range, long range, whatever, and they do not commute with each other. So, this gives you a model of a standard ergodic Hamiltonian. Okay. So, now we are going to drive this with a two-rate drive protocol, which has periods T1 and T2, and in this talk we are going to talk about the case where T2 is an integer multiple of T1. Okay. So, familiar examples are cosine and square pulse, and for most of the talk I am going to talk about the square pulse here. So, why this kind of things reduces heating? The simplest thing to see is to take a square pulse, where the first drive has a period of T1 and the second one a period of T1 by 2. So, essentially, if this is the case and this is my Hamiltonian, then I can write my Hamiltonian for any part of this, any instantaneous Hamiltonian as some A times lambda naught plus B times W1, where A and B could be 1 and minus 1. So you can just look at this and see that at any point. So, for example, here it's A equal to B equal to 1. So, the Hamiltonian is lambda naught O1 plus W1 O2. And for this part, I am setting W naught to 0 for now. Okay. Now, the evolution operator therefore can be written in terms of these. There are 4 of these parts of these cycles, and you can put them one after another, the standard trotter. And you see that they cancel pairwise, because if you change signs of A and B together, the Hamiltonian changes sign. So, this is an exact cancellation irrespective of the nature of the operators here, and therefore it gives you, so U becomes identity, and therefore your Fluke Hamiltonian vanishes, which essentially means that you have formed a perfect flat band at energy equal to 0. So, this is only a stroboscopic dynamical localization or freezing, because nothing moves stroboscopically. However, there is micromotion, so that has standard motion. So, you haven't frozen the system for all times, you have just frozen the behavior of the system at integer multiples of the drive frequency. Okay, I am going to skip this cycle, but you can do a much more general analysis and show that this can be done for a wide class of protocols with certain parameters, but let me just skip this for the moment. Okay. So, what does this dynamics look like? So, if you are at the flat band, your stroboscopic dynamics is completely frozen, and that is not so interesting, although it is interesting in the sense that it gives you an parameter regime where you can essentially arrest your heating exactly at stroboscopic times, because it is going to be repeatedly coming back to the same point. However, more interesting in my opinion is essentially the case where you study these systems not exactly at the frozen point, but around that. Because around that frozen point, whatever the Fluke Hamiltonian that you get must be proportional to the detuning parameter from the freezing point, because at the freezing point the Fluke Hamiltonian is 0, and therefore if you don't have a detuning parameter, your Fluke Hamiltonian just vanishes. So whatever that Fluke Hamiltonian is, it's just going to depend on this detuning parameter, which in our case is this W naught, and therefore for small W naught we get a perturbative regime which neither depends on the high amplitude nor on the high frequency. It's a completely different perturbative regime that one gets. And just to make this point, initially we are going to talk about this non-perturbative regime where my W1, lambda 1, omega 1, all these are set to 1. So this is as non-perturbative as it gets, and W naught is kept small. So here is this Fluke bandwidth that you see. So in a standard drive thing, if you have a Fluke bandwidth, that's just 2 pi in units of frequency, because you just uniformly distribute these quasi energies on a circle. That's a standard Fluke this thing. Here, if you are exactly at the frozen point, everything is concentrated on 0, and therefore the width is just 0. Okay. So this is plotted as a function of drive frequency, and this is true for any frequency. Okay. As long as you maintain the ratio of the frequency to be an integer for this square pulse. But in between, when you put this W naught, you see that you move from this frozen behavior all the way till the ergodic behavior over a wide range of frequency, this is the perturbative regime that I am talking about. So how does the distribution of these eigenvalues look? So of course, if I had a perfect single rate drive, for example, where everything is ergodic, you have a flat distribution of this Fluke eigenvalue, because on a circle they are uniformly distributed. However, here they have a delta function peak, and therefore as I move away by tuning this W naught, you see that the peak essentially flattens, and that's how you go from this completely non-ergodic to an ergodic behavior. So the point is that there is an enough range of this perturbation where you see a behavior which is not, at least for finite size system, violates Fluke ETH. Okay. So strong deviation from the prediction of Fluke ETH, which is realized for the single rate drive protocol. Okay. And all of this is happening because of this freezing, exact freezing point. How much time do I have?
We have time.
Okay. So then another way to see why this thermalization in this kind of things happen in slightly delayed way is to find out the spectral form factor, and this, as you know, has this famous deep ramp plateau structure, and this is a schematic behavior of the spectral form factor. But interestingly, this deep essentially tells you, so first you have this slope which comes to this deep. So this deep essentially tells you when this thermalization starts to happen. It happens in this ramp region, but this ramp region follows directly after the deep, so one can estimate the thermalization time by locating the position of the deep. Okay. Now this one can do a small analytical calculation. So you see that this spectral form factor is just the sum of this exponential of this Fluke energies, and if you are doing this at small time, you can sort of expand this, and then the sum over these eigenstates, that Fluke eigenstates that you need to carry, can be converted to an integral, and after doing some calculation, the result that you get is that the deep time essentially goes as inverse of the Fluke eigen spectrum length. Okay, so the extent of this eigenspectrum in the Fluke Brillouin zone, that's what gives you this deep time. And therefore, as I go closer and closer to this frozen point, which is this red dot, you see that the deep time essentially moves to larger and larger number of drive cycles. This also means that closer you are to this transition, this freezing point, you can delay your thermalization by an inordinate amount. Okay. That's one thing that tells you that this heating can be arrested. So correlations and entanglement also shows some interesting behavior. For example, they show a broad dip, and the entanglement never reaches the page value, it goes to some constant value, and we don't have an analytical understanding of this number, and so on. Okay, but it's just generally properties of this driven system in the perturbative regime. So now let me 10 minutes?
15 minutes.
Oh, 15 minutes, good. Okay, very good. So now I am going to use this model and drive it in the perturbative regime, and the reason I want to do that is what I want to show is that although this PXP model is a completely ergodic model and I am just driving it, apparently an emergent integrable model can occur in the Fluke sense from this driven ergodic model. So that's the main point of the talk. You see, in general, this integrable and non-integrable models are two cornerstones of Cornell's metaphysics. They are two very different kind of models. So what it seems is that a drive may provide a connection between the two. Okay, so that's the main message that I wanted to give. So, So what do? We take this model, this PXP model, and we try to calculate using Fluke perturbation theory, the Fluke Hamiltonian, and we do this order by order. And here my parameter lambda naught, which is the amplitude of one of the drives, is large compared to the other two problems. So we are far away from the non-perturbative regime that we are addressing, but here we have a finite W naught and a W1. So we are also reasonably far away from the frozen regime. Okay. So, however, once you do that, you see that the first order term is what I just showed before. It's just this sine gamma by gamma factor and some PXP terms. However, there is a second order term, and the form of the second order term is some sigma plus sigma minus is flanked by some projection operator, and then a sigma z tilde, which essentially means that there are two projection operator and there is a sigma z sandwich in between. So these parameters alpha out here is some 4 times gamma, and gamma is of course lambda times this lambda naught times the drive time period divided by 2 pi, or divided by h bar. Okay, so that's the parameter. So a alpha is some complicated function of alpha. Okay, so the drive amplitude needs to be large for the validity of this perturbation theory, and the Fluke Hamiltonian essentially vanishes at W naught equal to 0, because you can show that both of this n alpha and this depends on W naught, and this is precisely what I was telling, because if you are at W naught equal to 0, you are at the frozen limit and then there is no Fluke Hamiltonian. So the presence of this second order term is also different from analogous expansion in the single rate protocol, because in the single rate protocol there is a particle operator sigma z, which essentially makes the spectrum symmetric around D. You can show actually that the Fluke Hamiltonian anti-commutes with this Hamiltonian. So this spectrum is symmetric. So your energy, so if you have an energy eigenstate, quasi energy eigenstate with E, you are going to have one with minus E, and there is a large number of zero energy state. But this two-rate drive breaks this, and that's why you can have an even ordered term in your Fluke Hamiltonian. So so now let's see what the dynamics looks like. So to see this, we first look this consecutive level spacing ratio of this system, and we see that there are these sharp dips towards 0.39 at special values of this gamma, where this gamma is integer multiples of pi, so that HF2 controls the dynamics. Okay, the first order term. Sorry, 10 minutes. Okay, thanks. So it seems that if you are just analyzing the spectrum at this large amplitude limit, you are going to find that this mimics all properties of an integrable model. Okay, so this is the dip which comes to close to 0.39, and there are some peaks which goes to 0.52 right after, and so on. Okay. So the other thing that you can, so essentially this has a characteristic of this of an integrable Hamiltonian. Yeah, so this is related to the fact that for large range of gamma, the effective model, which I haven't shown here in details, mimics a PXP thing, and in PXP thing finite size effects are strong, and they are, even if you do a single rate PXP at this level, it comes to roughly 0.44 R. So this is a finite size effect, why it goes down. Okay. So if you go to 32 or higher system sizes, which we haven't, there are some older papers, and there you can sort of see that it moves towards 0.5. The other thing that happens here is the longitudinal magnetization remains conserved at these special points. So here is the plot at gamma by pi equal to 2. You see that it's a flat thing for close to -1 for the vacuum state and close to 0 for the Z2 state. Whereas if I just move away from here, there is magnetization dynamics and they go to their respective predicted values for the PXP model. Also, if I look into this mz as a function of lambda naught by W1, what I find is that it remains constant only in the large drive amplitude regime, and this thing breaks down in the small drive amplitude regime, showing the perturbative nature of this. Okay, so now why is this second order Fluke Hamiltonian integrable? So I am going to take the next 5 minutes just to explain this, and that would be the end of the talk. So the short answer is that at least in the k equal to 0 sector with periodic boundary condition, we have an exact mapping of this Hamiltonian to an XXZ model. Okay. So this model, this mapping involves deleting downspins to the left of every upspin on the PXP model. Okay. So if there are n upspins in your system, your chain length goes from L to L minus n, okay, something like that. So now how do we show the equivalence? First let's take the simpler thing, which is the diagonal term. So if you write this diagonal term, and you do some algebra, you can show that because this is sigma z tilde, you can write it in terms of some term which counts the number of downspins, which is this 1 minus pj, and some other term which is finite only when it has a combination of this up down now. Okay. Because there is this 1 minus p, then p, and then 1 minus p, and that's what's going to. The first term is a constant. Okay, because these do not change the magnetization and do not change the number of up or down spins. This transformation conserves it. The second term, now think of it in the PXP XXZ language. So what we do, we delete our down spin to the left of an up spin, and therefore this configuration of the PXP model goes to a up configuration in the XXZ model. And this term essentially counts that up configuration. Okay, so there is a natural mapping between this sigma z tilde operator to a 1 plus tau z and 1 plus tau z kind of combination that is here. Okay, and therefore if you just take delta to be some particular value which is determined by these factors of 4 and n and stuff like that, then you can show that there is a 1-to-1 mapping between the state sigma of the term sigma z tilde and delta. But this is of course not all, because you have the off diagonal terms, and that's a more difficult thing to do. So for the off diagonal term, what we do is that we show that the matrix element of this off diagonal terms of the PXP model in the PXP basis and of the XXZ model in its Hilbert space basis, they are identical. So how do we show this? So what we do is that we first look at this Fock space, and because we are in the k equal to 0 sector, we can take superpositions. But these Fock states essentially have a particular periodicity. So spin patterns might repeat. Okay, so we call that periodicity to be R1, and this in this diagram R1 is 3. You see that this pattern keeps repeating. Okay. Now number of upspins in each block is something we called M1, and in this picture M1 is 1. Therefore, the length of the chain is the number of blocks is L, and therefore the number of blocks is L by R1. Because if you have a periodicity R1, the number of blocks would be simply L by R1. Number of upspins is N1, which is the number of upspins in each of these periodic blocks times the number of blocks, which is M1Q1. Okay, and we also denote M0 to be the number of flippable spins in each block. Okay, you can only flip them when they are flanked by some 2 down operators. So if you construct a state, a generic state in the k equal to 0 sector using this periodicity, and take its matrix element between these 2 states, you can show after some calculation that it just depends on the ratio of square root of R1 by R2, and since L is a constant and we have this, it depends on the ratio of square root of Q2 by Q1. Okay, that's the thing. Now here, now let's come to the other side, the Hilbert space. So when I delete this thing, my Fock state periodicity changes because it becomes R1 minus M1, because if there are M1 upspins, I am going to delete one block, one spin on its left, and therefore this block is going to reduce in size. Okay, the number of upspins remains same because I am not deleting any upspins. The length of the chain now decreases, of course it's L minus N1, but N1 is simply this M1, which is the number of upspins in each blocks times the number of blocks. Okay, that's there, and this is Q1 times R1 minus M1. However, now if you look at the number of blocks, which is this L minus N1 divided by R1 prime out here, it's still Q1. Okay, so conserves the number of blocks. And because this answer only depends on the ratio of the number of blocks, the answer to this becomes identical provided you set this j to be n for 4n pi, n of 4n pi by 2, and therefore this leads to delta equal to half. Okay. So essentially this model can be mapped directly to a xxz model with delta equal to half, okay, and that's why it's integrable. In other sectors, there are other ways of proving its integrability, but there is no mapping to the xxz chain. Okay. So the last thing, 4 minutes, yeah. So the last thing is that xxz model of course has several higher conserved charges, and one of the things that we know is that the third conserved charge, which is this cross product when this dot, okay, this is sort of the chirality kind of operator, and this we can write down in this manner using this tau plus tau minus etc. So now to see what is that conserved charge in the PXP language, we can do the following. So we find out these two states 1 and 2, which is connected by say one of these T1, okay, and this has a down and a up, and this is converted to a up and a down by this operator out here, okay, and tau z is set to down for the moment, okay, let's say. Now we back construct the state of the PXP, which corresponds to these states by simply putting a down spin in additionally to the left of every right spin, because those are the spins we have deleted, right, to construct the xxz chain. Once we do that, then we find out an operator which connects between these two states, okay, and we do this for every of these terms, okay. So this so you have a O1 where this alpha is down, and then you have a O1b where this alpha is plus, and some more calculation which Shaptadeep did very painstakingly apparently gives you all these terms. And now you need to choose a linear combination which respects the odd nature of this operator, because C3 is odd under parity, and also it has to commute with HF2, okay. So you do that, you construct that operator, and one can show that it indeed satisfies this property. But now, how do we know that it's a conserved charge? So what we do is that we compute the Frobenius norm of this commutator with the full HF numerically, which again Shaptadeep worked out, and you see that at these special values there is this dips and it really goes to 0, showing this emergent conservation of the third charge in this integrable model. So magnetization is the first charge, Hamiltonian is the second, and this is the third, and therefore all this so I'm done. So yeah, so I'd like to say that this drive essentially gives you a way in the second part of the talk, gives you a way to connect between the integrable and the non-integrable models, and this is a bridge which is only possible due to dynamics. So I think I'm going to stop here, and thank you for your attention.
We have time for just 1 or 2 questions.
Yeah.
So you said that away from the freezing point in the spectral form factor, it simply gets delayed depending on the distance from the freezing point. The ramp and saturation gets delayed,
yeah.
but eventually reaches the same ergodic value at long times.
Yeah, of course. If you continue, it will first thermalize and then reach a plateau.
But then you showed another curve where the magnetization is just saturates to a non-thermal value and
no. Sorry, you were talking about this, right? Where it's no. This is sort of okay. So the reason why it saturates. So first of all, this is a driven system. It goes to some what do you call this, diagonal ensemble value. But this is a bit more than that. So this diagonal ensemble value where it should saturate according to ETH is this dotted line. Here this happens because they have scars, and this scars gives you this super thermal value. Whereas here, starting from the ground state, it's subthermal value, which is something we saw before, and there are reasons why it happens. Okay.
So generically, it would reach the
yes.
Can I take that question first, and then I will come.
Yeah.
So I just want to ask that this connection between the integrability and non-integrability because of dynamics is happening specifically because of the Floquet technique that is
That's right.
And in any other quenching scheme, okay, maybe quenching or something may happen.
We haven't really explored that. I don't really know. But the point is that you see here there is this emergent phenomenon which is an approximate emergent quantity where HF1, which is a local thing, controls the dynamics. So that is very crucial for having any of this phenomena. However, in this kind of quench, I don't know of an analog of that. I mean, that's the.
And any okay. So if I'm understanding correct, it's also this kind of flow-key driving where you have two rates and the way you drive this. Otherwise, if I do a normal flow-key, for example, with any cos or
No, you can, except that there is a drive where you do a square pulse, but a sort of asymmetric square pulse, where you will see a phenomenon like that. I haven't shown that here because of lack of time, but there is also another way of doing this actually. Yeah.
So I had a
Yeah.
question. So this connection between non-integrable and integrable systems. So is it specific to the PXP model, or do we have reasons to believe it might be more general?
As of now, what we know is that we only have this at this model. Okay. But in principle, it might be more generic actually. One can engineer in principle, but I haven't really thought very deeply about that.
But it's conceivable that there should be a unitary that takes me between the eigenstates of an integrable
Yes.
to a non-integrable.
No. But look, this is not an exact integrability. So that unit. So what that unitary can do is to give you a dynamics which is very similar to that of an integrable model. Okay. So that's the claim that we are making. And if you are sort of looking into a large drive amplitude regime, that regime is very long. Okay. So that's my claim here. I'm not claiming that this is exact or anything like that. Okay.
So, are you done? No, I had just one more question. So you had two operators there, O1 and O2, which you said they
Yeah.
can be non-commuting, but if they are commuting, that's just like.
No, but if they're commuting, it's trivial. That's the point.
But they're two independent like drivers.
They are two independent operators, and the generic case is where they don't commute, and it's only then you are going to have a non-trivial Hamiltonian. Okay.
So is it important to have the ratio of the two frequencies to be integer, or can you see integer?
It depends on your drive protocol. It has to be an odd integer if you are doing cosine. It has to be some integer if you are doing. Otherwise, these two-rate protocols do not give these properties actually.
But this quasi-integrability, does it stops heating completely, or?
It will stop up to some
Does it
pre-thermal
increase the
time.
time compared to the case where
No,
you have
it will reduce.
technical localization but not integrable?
No, that I don't know. You see, the heating reduction part is based on when you are near the freezing point. Okay.
So freezing, what you're saying is actually the dynamical localization, right?
Freezing is like dynamical localization or freezing or whatever you want to. The Ornov is not happy probably, but this is sort of is just a statement that U becomes identity at the end of the this thing. So it's different in that sense because it holds for all operators. It's not
Specific.
not a specific operator. Yeah.
Any other question? Last question.
Sir, so in terms of like the first case that we considered, there were O1 and O2 operators, and like the Thouless time is delayed as we go away from the freezing point. So in that case, does the nature of O1 or O2 has any effect on it? Like suppose if we have a longer range operator, like we
Yeah.
that to be more chaotic in nature.
That will be more chaotic. Actually, so we haven't really studied this in detail. We only studied this model, but usually you expect that for a given system size, longer range operator is going to destroy this more effectively compared to, yeah, sure.